So about 13 years ago, I was gifted this electromechanical robotic arm, which has no sensors, no servos or encoders. And the hope was I would interface it with the TI-99 for a computer, which is right here. And I did just that at the time, using assembly language and an interface board that I created, which basically converts the parallel port inputs into actionable current voltages and selections through relays and Darlington transistors to power up selectively the motors on the arm. I'm not going to go into any further details. I'll link the original video in the video description below. So what I did this current iteration is a natural continuation of the previous experiment, where at this point I added limit switches to the arm in order to be able to provide automated initialization of the position. So I have a switch here, a switch here, a switch here, a switch here, and a switch here. Each one of those limits the movement of one motor. So this one is for the base rotation. This one is for the main arm here. This one over here is for the secondary arm. And this one is for the claw arm. And then the one inside here is to detect the opening and closing of the claw. With this available now, we can automatically initialize the arm to a known fixed position, and then from there we can program it to move to any other position we want. So why don't we go ahead and initialize it. We've got the UCSD Pascal control program here. I'm not using assembly this time, just being lazy and just using Pascal. So if we press I, it will automatically initialize. There we go. Okay, so that is the initialized state. Now, next step would be to demonstrate programming the arm. Alright, why don't we give it a try here. Let's program it to pick up this piece of foam from this position and place it approximately in that position. So we'll start by selecting first initializing. It is actually in the initialized state right now, so we're good. We'll start recording mode, and let's see. Here. Okay, let's open the claw. Okay. That looks good here. Alright, and if we close, it should close on it nicely. Let's try. There we are. Okay. Let's up a little bit. Oops. Okay. Get the arm out of the way now. Okay. So we'll turn recording off. Let's put the foam piece back here. Hopefully when it it stays up in an upright position. Okay, ready for playback. So first it will initialize automatically, and then it will play back the recorded motion. Let's see what that gets us. Here we go. Takes a few seconds here to start the playback. Alright, well, I will take that as a success. As you can see, it's quite sketchy. Again, there's so much variability with the motors and the inertia effect, and frankly I think some of the motors are starting to show some stress signs that have been used for hours and hours between the initial experiment 13 years ago and the current one. And I think we're probably going to be retiring the arm at this point. In any case, that's the programming function, so it does work, you know, albeit fairly rough. Alright. So you might ask, is there a way to give the robot arm a set of three-dimensional coordinates in the XYZ dimensions and have it calculate the path to reach that targeting point as accurately as possible? And the answer is absolutely yes. And actually the robot arm control program does have a mode called targeting mode, which allows you to enter a set of coordinates XYZ, and it will calculate the different angles each part of the arm, each joint of the arm has to move to in order to reach the target. Unfortunately, there are two problems with this. One is that it takes quite a long time to actually do the calculations. I'm doing it iteratively, where basically one arm is moved a little bit, then the next arm in the sequence is moved throughout its entire range, and at each point we're testing the end point, which is the tip of the claw, versus the given set of targeting coordinates, and so on and so forth through all the joints. So as you can imagine, this takes a long time. There is probably a better way of doing it, but that's the solution I came up with. In any case, we can actually do a demo here to show you. But the second issue, of course, is beyond, while it does the calculations correctly, unfortunately when it executes them, there is the accuracy is very, very poor, and the reason for that is primarily because the motors inside each joint are not servos, and there are no optical encoders, so there's variability in speed at each of the joint depending on the load, on the position, on the current draw, etc. So lots of variabilities that add up to significant errors. The longer the path, the more the errors, and we can actually go ahead and do that demonstration. I picked, let's pick a point here in front of the robot, this point here, which is at coordinates minus 5.4 in X and 21.5 in Y, and we're going to use this red foam cube here as a target, which is about 2 centimeters in height. The calculations are going to aim for about an error of plus minus 0.5 millimeters in the distance between the robot arm and the cube and its height. So now, going back to the program, if you press T, it'll ask us, it'll be target mode, and we're going to initialize because we're starting from scratch, so we'll say yes. And go ahead and do the initialization as before. We'll wait for it to be done. And now it'll ask for the x coordinate, so it's going to be minus 5.4, the y coordinate is 21.5, and the z coordinate is 2. And it's going to target the half of the height, so that it grabs the object in the middle. And here we go. So the calculation of the rotation of the base is very quick, so it already has done it and it has rotated the base. So now we're waiting on the calculations for the rest of the arm extensions, and that's the part that takes a long time. So we'll go ahead and let it do its thing, and we will come back to it. Alright, so we're back, and as you can see, the calculations are done, and it took 3.6 hours to calculate the various angles for the arm. So these are all in degrees, so the base angle is minus 75.9 degrees. The first arm is 60 degrees, third arm is 10 degrees, and the fourth arm is 65 degrees. dx is essentially the error measurement between the actual calculated distance of the target from the center of the base, and that's 0.3 centimeters, which is within the 0.5 centimeter error margin we established originally. And then y is the actual height difference or error, and it's 0.5 of the original height of 2 centimeters. Okay, so now we're gonna press enter and we'll see where that lands us. Alright, and that's it. And as you can see, we are quite short. We're in the general direction for sure, but we're at least, I would say, 3 centimeters maybe off here, and the height is definitely too far down. It's actually going technically under the surface. So that shows that there is definitely errors, accumulative errors in the movement of the arm because of variability in the various motors speed, as well as the torque applied to each arm depending on where each of the arms is. Gravity may actually accelerate the rotation, whereas if we're trying to raise an arm against gravity, that might slow the rotation, etc. So to verify that our calculations are actually correct, we can actually reset the arm and use a common protractor to actually set the angles exactly as indicated by the calculations, and see where that ideal setting lands us. Okay, so I've initialized the arm, and in the initialized state, the base is at 90 degrees straight up, like that, along that line here. The arm here, called arm 2, is at 160 degrees, with 90 being up here and 0 being down here. Arm 3, which is this arm here, sits at 90 degrees straight up when it's lined up completely with arm 2, with 0 being up here. And finally, arm 4, which is the claw arm, again 90 is in line with arm 3, and 0 is down here. So why don't we go ahead and start? So the base angle was minus 75.9, so anything to the left of 90 is negative, and to the right it's positive. So 75.9 from 90, so that puts us at only 76. Basically, it's not very accurate. So if we line up the protractor with the line, that's about there. Okay, we're gonna go ahead and go into manual mode and move the base to the left until it's about, in there, hard to tell. I think it needs a little, yeah, that's about right. So that's the base, and then let's adjust arm 2, which is this arm, and that's calculated at 60 degrees. So 60 degrees is basically 1, 2, 3, 4, 5, 6. So here. So we'll actually, let's do arm 3 first. Or no, let's do arm 4 first, because otherwise things will touch the table. So arm 4 is at 65 degrees. So that puts us, if this is 90, 80, 70, 65, and that's the axis here. So let's do that. Let's make sure we're as accurate as we can be. Okay, that sounds about right. Okay, arm 3 is at 10 degrees, so 90 is here, so 10 degrees would be essentially here. So it needs to go up to here. Alright, let's make sure this is as perpendicular as possible. 3. There. I mean, this is fairly rough, but I'm eyeballing it here. Okay. Alright, and then arm 2 is at 60 degrees, which is this arm here. So 60, 1, 2, 3, 4, 5, 6, so about here. So I'll try to keep it as accurate as possible. So 2. Oops. Oh shoot. I moved that arm, didn't I? There. Okay, we are at 2. And let's move it to 60. That's about 60. There we are, exactly. And as you can see, with the right angles chosen as calculated by the program, we are pretty darn close to the center here. Again, there are some significant inaccuracies with my measuring and with the initial angles, probably off by a few degrees, but as you can see, it's if we take this off, it's really, the X is here, we're practically right there, and if we look at the height, it's well within the 2 centimeter error margin here. It's about 0.5 centimeters actually, which is exactly what we got. So yeah, this shows that essentially the calculations work, but given that the arm is electromechanical, we don't have any encoders and there are no servos, it's really difficult to accurately position it accurately. But yeah, so this is what it is, and the fact that we actually can get there is pretty interesting by itself. All right, so that's essentially all there is. I hope you enjoyed this brief discombobulated video, and thank you for watching.